Today I will talk about numerical estimation of crack opening. It's a work that I've done with my previous advisor, like Farid Benboudjema and Xavier Jourdain and Fabrice Gatuingt. Today I work for EDF, like Jean-Luc is one of my colleagues, and I will talk about nothing about EDF, but only about work of my PhD. So a bit of context, as you all know, cement material is widely used, cement-based material is widely used, and concrete material too. And one of the major issues of concrete and cement material is cracks, because it may induce durability issues. It may favor penetration of aggressive spaces like chloride, carbonation, and so on, and sometimes allows leakage. The crack is also a multi-scale problem because it goes from the component like the CSH, the aggregate, and it's also a macro-scale problem. So it's a bit difficult to model, and there are different approaches to model crack in concrete material. Okay, so there is different approach and different complexity, whether the modeler are interested in the incompatibilities, structural application, and so on. And there are two different classes of model. The model that based on solid mechanics, like discrete modeling and other models, and model based on continuum mechanics, like damage modeling, IFM, XFM, and so on. Damage is often an approach really used in the modeling world of cement material because it is affordable regarding calculation time, and it's allowed to capture the failing process of the concrete material. But in this approach, cracks are not modeled explicitly. We only have diffuse microcracks. We don't have cracks, but we have only diffuse microcracks with the damage index. So to get some crack opening information, we need some tools, some post-processing technique to calculate cracks from damage index. As an earlier study, Matana and al. Propose a post-processing techniques for mechanical loading only. It is based on the decomposition of the total strain into an elastic part and an inelastic part. And then with a characteristic length, like for instance, the length of the element, it's able to compute a crack opening. But it is based only on mechanical loading, and the question is, what happens if other strains are added? Like for instance, when you model shrinkage, you model creep, and so on. With this approach, there is a problem. It gives not or an underestimation or overestimation of the crack opening. So to answer this question, we take a classical damage mechanical model, like the first one proposed by Mazar, the isotropic damage model, that links the stress to the strain with the four-order tensor C, the stiffness tensor, and a scalar variable D that reduces the stiffness. The evolution of this damage variable is taken as proposed by Fenstra for the damage variable intention. And in order to prevent mesh dependency, we use an energetic regularization as proposed by Hillerborg that links the amount of energy in each element, that links the amount of energy of each element of the size of the element. So let's go into the crack opening extraction model. The main principle is to calculate the Perhaps it's a bit blurry for you. I'm sorry. But the main principle is to calculate epsilon f that represent the analytical strain. And we calculate this value from sigma 1, which is the result of the structural equilibrium. So there is already all the deformation taken into account in the modeling are already considered in this sigma 1. So what you can see the techniques, the post-processing techniques. It is based on 4 stages. The first one is to compute the total strain from the damage index, the compliance tensor, and the total stress tensor. Then we are able to compute the elastic strains from the undamaged compliance tensor. And finally, we are able to compute an elastic strain. And with the computation of length, characteristic length, sorry, we are able to compute a crack opening. So let's see some practical case study. So the first 2 practical study are rather simple case study. So we consider 2 imperfect rods under different type of loading. The first one is free to deform, and the second one is restrained. It's composed of 10 elements of the same size, same material, except one, the number 6, for example, which is imperfect. Its tensile strength is equal to 50% of the nominal tensile strength. We set a bunch of mechanical parameters like the tensile strength, the Young modulus, and so on. And we apply 2 fictitious loading. The first one, the blue one, is the fictitious drying shrinkage, and the second one is thermal strains due to the evolution of temperature, for instance. And then we compare to the theoretical expression of crack opening in 1D. So let's go to the results. On this plot, you can see on the left side the result of the rod under without the rod who is allowed to deform, and on the right side you see the result with the rod restrained. As expected, when the rod is free to deform, there is obviously no crack because it is free to deform, and the theoretical value is equal to 0 all along, and the proposed method is also equal to 0. However, you see that Matala and Al first post-processing technique give something different from 0. When you consider restraint condition, you see that the proposed method follows the theoretical results, and there is a gap between the method proposed by Matala and the theoretical value. So on this case study, the proposed method fit the theoretical solution, and Matala post-processing techniques is not far, but is not suitable for our application. The second practical case study is a bit more not complex, but we try to go further. So we investigate the response of the post-processing technique on a shear wall under drying. So Sazano and al. In 2018 did some experiment on shear wall to solicit this wall under dynamic loading. So the dimensions are given on these figures. So it's a wall that is 2.5 meter high, 2.5 meter wide, and 0.7 meters depth. There is two stub on the top and on the bottom, and there is a wall between these two stubs. The entire wall is reinforced with rebar, and there is two steps. The first step is the aging of the wall under 58.7% relative humidity and 18.4 degrees Celsius for 1 year. And then there is the dynamic loading. In the study, I focused only on the aging part of the Sasano study. The interest of this study is that Sasano monitored all the cracks during the aging and the loading phases. They also provide companion sample that allows us to calibrate our hydromechanical model. So to age this wall, we need an hydromechanical model. We use our mechanical model, but as soon as the hydromechanical, thermohydromechanical model use damage variable, it is possible to did the same study. So I won't go into detail because it's not the purpose of this presentation, but in this model, we have the first stage with mass balance equation, equilibrium equation. Then the drying shrinkage, the one proposed by Biot-Coucy. We use, according to Creep, a burger aging materials, and the drying creep is taken into account with linearly with the links between drying shrinkage and drying creep with the lambda coefficient with a scalar variable. Sorry. Then the mechanical model is a mechanical model that takes into account the capillary forces and the effective stress, take into account all the added deformation. This model needs to be calibrated. So the study. So the first stage was to calibrate the drying behavior of the material. So see that the calibration is rather good. Then drying shrinkage was also calibrated, also a good prediction. And then we use dummy specimen. The dummy specimen was slab companion samples that we simulate and we adjust in order to be to have the best calibration possible. One drawbacks of the study of Sasano that was there were no regards regarding creep. So to account for creep, we had to take a constraint from our database with a mix close to the one you call parameters. They were calibrated on compression and bending samples. So for instance, you see the evolution of different bending sample. So there is the applied load versus the crack mouth open displacement, and you see the calibration for the wet sample in blue and the calibration for the dried sample. I don't go into more detail about calibrate parameters. They are all available in the conference paper if you are interested. Another important point, in order to favor the localization of the cracks, we use a random fields on strength resistance, the one proposed by Materon, the turning bend methods. with a coefficient of variation of 10% and a correlation length equal to 3 times the biggest aggregate. The biggest aggregate was equal to 15 millimeters.
Francois, quick comment, 1 minute left.
Yes.
Thank you.
Yes. So some details about the modeling. Rebar are elastics, and it's assumed perfect adhesion between concrete and rebars. Let's go into the last slide. On the top, you can see the experimental cracks, and on the bottom, the numerical cracks. About the localizations, we can see that diagonal cracks are partially reproduced. It's a good features. We reproduce the cracks at the interface between the stubs and the walls, but columns, the cracks on the columns are harder to model. About the crack width opening, on the experimental value, we found value between 10 and 150 micrometers, and in our modeling, there's 10 micrometers maximum. This is probably due to the hypothesis about the bound relationships between the concrete and rebars. So, some take-home points to conclude this presentation. So, crack is an important feature of concrete material, and it's often modeled with damage approaches. One drawback of these approaches is that crack is not explicitly available, so we have to use a post-processing method. Our method was tested and validated on simple tests, and we try to confront this method to a semi-structural application. Of course, it's not perfect, but the routine managed to locate area where crack develops and slightly underestimates crack opening. This simple post-processing method is compatible with other multi-physics models as soon as there is